So the next thing we're going to do is we're going to use our information that we know about the elements, most of the time specifically electronic configuration, but also some of the properties of the nucleus, to develop periodic properties, or properties that we can use the periodic table to distinguish from element to element. One such example of a periodic property would be ionic size, or size of an ion. And here's an example of where ionic size, the size of the ion, is very important. So here we have a representation of an ion channel pump within a cell membrane. So here's our bilipid structure that composes cell membrane. And here we have a couple of proteins, 3 proteins that form a structure that can pump ions in or out. Okay, now depending on what side of the cell we're talking about, either intracellular or extracellular, at various points in say muscle movement, we would want to pump sodium ions out of the cell and potassium ions into the cell. Okay, now how does this protein ion pump know what ion to pump in and pump out? And of course that comes down to with the size of the ions. Sodium ions and potassium ions are different sizes, and based on that property enables the protein to push or the specific ions in or out of the cell. Okay, so we're going to look at several different properties of the elements, and we're going to use our information both quantum mechanically and experimentally to determine these properties. Now, Dmitry Mendeleev showed very early on that he was able to predict properties of various elements to very quite well determinations, predict properties of specific elements such as melting point or density or formulas, to a great approximation to the actual properties. And this was, of course, long before the instrumentation that we have that we can actually measure mass down to the atomic mass units. He was very good at showing how powerful the periodic table is. One additional aspect of electronic configuration that we're going to need to discuss first, though, is a 4th quantum number, or the spin quantum number, m sub s, also known as just the magnetic spin. Now, it turns out that this magnetic spin doesn't come right out of the Schrodinger equation. Actually, can be determined experimentally. And basically, if you pass a beam of atoms, it turns out that the electrons are going to be either attracted to the north end of a magnet or attracted to the south end of the magnet. And so what you get is you can split the beam into 2 parts based on their magnetic spin value. It can either be positive 1/2 or negative 1/2. Okay, so the next thing we're going to want to do is we're going to want to develop a way to express all 4 quantum numbers that we now know, and that is through the orbital diagrams. Very similar to electronic configurations, only slightly different. Okay, what we have now is magnetic spin, 4th number, can either have positive 1/2 or negative 1/2 values. Okay, if it is a positive 1/2, what we're going to do is show that as an up half arrow in an orbital block. If it is a negative 1/2 arrow, we will show that in the as a down half arrow in the orbital block. Okay, so report down half arrow. There we go. Okay, so what we have here is a very simple orbital diagram for hydrogen. Okay, we can see the n number here, 1, the L value as S. For each m sub L value, we're going to draw a box, and then of course the m sub S value we will draw as the up or down half arrows. Okay, now we already know that 2 electrons can fit in an orbital, and if we are going to place 2 electrons in the same orbital, the spins must cancel or they must be paired. So for helium, we would draw a 1s, our orbital diagram, and a up arrow and a down arrow to show that the electronic m sub S values are canceled. One is plus 1/2 and negative is, or the other is minus 1/2. And that stems from the fact that that no two electrons can have the exact same set of 4 quantum numbers, and this is known as the Pauli exclusion principle. So if you have 2 electrons in the same orbital, they must have different m sub s values, because the other 3 quantum numbers will of course be the same. So as we go forward developing orbital diagrams, it would be important to remember that we can figure out how many electrons are held in energy levels by our good old 2n squared rule. There's 1 orbital in the s value, so there's 2 electrons there. There's 3 orbitals in p, so we have 6 electrons there, 5 in d, 7 in f, and then of course 10 electrons and 14 electrons. So for the p orbitals, we would draw, of course, 3 boxes for our 3 m sub l values. Okay, and we'll take a look at what those look like next.